I was Julian Abrego, everyone.
Sir, no.
All right. So we're going to do more with Riemann sums.
No.
What do you notice?
We have a
table instead of a graph, right?
No.
So this is just data. So we're given a table of data. We've got x values and function values. Okay? And we're going to use a Riemann sum to approximate the definite integral. Okay? Now, so first off, it says the integral from 0 to 6 of f of x dx. So again, we have our x values and our function values. It says using a left Riemann sum with 3 subintervals. So we're going to take our data here from 0 to 6. And notice it's nice and even. It's 0, 1, 2, 3, 4, 5, 6. They're all the same space. And it just goes from 0 to 6. So that's our integral. We're going to break this into 3 equal sections. Okay? So if we break into 3 equal sections, we go from 0 to 2, from 2 to 4, and then from 4 to 6. So those will be our 3 equal sections. Okay? Now for our left Riemann sum, remember we picked the left f of x. So we're going to start at, well, our first will be 0, right? And then our next would be 2, and then 4. Okay? So remember it's a left, so we're going to leave off our last endpoint. We're only going to have 3 rectangles here. Okay? So using just simple notation, I'm just going to call it L of 3. So the left Riemann sum with 3 subintervals. Now, how wide is each of these rectangles? 2. So we're going from 0 to 2, 2 to 4, 4 to 6. So how wide is each rectangle? 2. So we've got 2 times, and now we take our first function value, so that's 7.6, plus our next function value, which would be 6.4. Remember our subintervals here, we have 0, 2, 4, 6. So right now, 1, 3, and 5 aren't going to be used. All right, so we'll have 6.4 plus 4.5. Okay. So calculators can come in handy. We get 14 plus, right, 14? 4.5, so 18.5 times 2, so we get 37.
And it's not equal. What's that? Where'd you get that equal?
Well, this is, I'm calling this L of 3. This is the left Riemann sum. The left Riemann sum equals 37. Oh, you get what from?
Yeah.
The 2. So that's the width of each rectangle. So we're going from 0. So this is, think of this as a rectangle. A rectangle. Did I graph them? No. So we don't have to. If you find it helpful, you can. But I've seen in the past where that leads to some confusion as well, for various reasons. So, because sometimes these numbers, like right now, decimals aren't really necessarily easy to graph, and then big and small numbers aren't really easy to graph. So sometimes you get really hung up on the graphing, it'll throw you off. So if we just look at the data itself, and we break it into 3 equal subintervals, just remember the left Riemann sum, we use the leftmost from each interval. So for the right Riemann sum, we'll use the rightmost f of x value. So I'm going to call this R of 3. Now again, our rectangles are still 2 wide, right? Because from 0 to 2 is 2.
This time we start with 6.
So this time we start with 6.4. We'll use 4.5. And then our last one is 3.4.
14.6.
So we add all these up, we get 10.9 plus 3.4, so that's 14.3, double it, so we get 28.6. Okay. Now look at the data in this table. Look at the data in the table. Is this function, based on just this data, is it increasing or decreasing? But based on just this data, it's decreasing. Okay, so we don't necessarily know that it's doing this, because in between 5 and 6, it could shoot up to 3 million for all we know. Okay, so all we know are these. But based on the data, it appears to be decreasing. And so would the left Riemann sum give us an overestimate or an underestimate? Okay, so the left would give us an over, so we get, notice the bigger number. The right Riemann sum will give us an underestimate. And so what's going to be right in the middle? The mid Riemann sum. Okay. And also the actual integral. So I'm going to call this M of 3 for the mid Riemann sum with 3 subintervals. What if I wanted 6 subintervals? What would I write? I'd write m of 6, and then each one of these would actually be an interval.
You just add together.
Right, so we would just add them up. Okay. What if I wanted 2 subintervals? Yeah, so we'd go from 0 to 3 and 3 to 6. What if I wanted 12 subintervals?
Half.
From one, I mean,
Zero to one
to
half, one half to one, one half.
That would be true, but if I wanted 12 subintervals, I would have to say, I'm sorry, I can't do this that problem.
You're only
You
given
don't know
six, 'cause
that,
you only
that's
have
that
six.
function.
I don't know what's happening at point 5. Like I say, at 0 we get 7.6, at 1 we get 7, at a half, but at a half it could jump up to 1700. Okay, there's many times when you're collecting data where at full hour intervals, certain things happen. Think about traffic. At 8 a.m., there's a lot of traffic. At 8:30, there's sometimes none. It depends on where you are, right? At 9 o'clock, it's packed. At 9:30, suddenly it's empty. At 10, we'll go in the hallways. Every 50 minutes, hallways are packed, right? But in between, not many people in the hallways.
There's a lot of people.
There's more than there should be, but it's not packed, right? So if we're collecting data in the hallways and we just happen to do it every 50 minutes, you would say the school is always crowded, the hallways are always crowded, right? That'd be misleading, because most of the time they're not, right? There's only these 5-minute intervals every 50 minutes when they're just packed. So for all we know, in between here, these numbers could be 0 or 2, or they could be 3 million. So if I said do this 12 subintervals, you can't, because we don't have the data. Okay? But if I do anything 6, 4, could I break it into 4 subintervals?
No, yes.
Well, is 6 divisible by 4? No. So since I have data for 6 points, I can't divide by anything other than divisible, right? So I can do it into 2, I can do it into 3, and I can do it into 6, right? That's the general idea. Huh? Or, yeah, I could do one big interval, and then my left would be this, my right would be this, right? Okay. Mid, though, I've got 3 intervals. Now, for this, I'm going to use the midpoint of each, right? Notice from 0 to 2, what's the middle x value? 1, so we're going to use this guy. And then we'll use this guy.
Is that really the midpoint?
And then we'll use this guy. It's the mid-Riemann sum. Now remember, it's f of the middle of the x. So halfway between 0 and 2 is 1, and f of 1 is 7.
Half of the middle of the x, not half of...
Not half of the y. No, it's not the average of the function. It's, okay? So we would use, now our bases are still 2, right? Rectangle is still 2, but now we would have 7 plus 5.6 plus 4.1. Okay? So adding these up, we get 12.6, 16.7, so 33.4. Okay. Now notice again, where does the mid fall but as far as the left and the right? It's between them, right? Is it halfway between them? No. Okay. Not necessarily. That's a really good question. Oh yeah, there are occasions where it could be.
But does it matter?
That's a coincidence more than a common. Okay. So that's it. That's how we do these problems.
That's easy.
Fairly straightforward,
Yeah,
right?
if we get to...
So now notice on this, how wide is each interval on this?
3.
So each one is 3. So if we break this into 4 intervals, notice we would have, there's 1, 2, 3, 4. So it's only giving us enough information to do 4 intervals right now. Okay? Now, when you get to the mid, notice suddenly the number of subdivisions changes. There's a reason for that, and I think whenever you do it, you'll understand what that reason is. Okay? So you've got the rest of the period to work on these.
We don't have a midpoint.
We don't have a midpoint.
Yep, so you have to change it. Okay, so you got the remainder of the period to work on this.